I'm going to be talking about the evolution of the fault networks and rift systems with surface processes. And for the most part of this talk, I wanted to focus on how the fault network changes as the rift evolves, and then a little bit at the end to see what kind of structures or sedimentary structures we can begin to see in these models. So to start, I wanted to give a very broad overview on the different types of rifts we can have. So if we have deformation that's localized in a very narrow region, we can get a narrow rift. And then whether our faulting is symmetric across the rift axis or asymmetric, we can get a narrow symmetric or narrow asymmetric rift. On the other hand, if we have, say, a weaker crust, we might get more widespread deformation over a very large region. In this case, we would get a wide rift. And then as you would expect, we have rifting that kind of starts in the center and then moves outward and deactivates over time. And this kind of records the history of these rifting events, which would be our passive margins that you could kind of see here. And this is something that people look into with seismic data. And so when looking into this with seismic data, they found that based off crustal thinning patterns, you can actually divide these passive margins into a few different domains. First, when you don't really have much crustal thinning, but you still have some structures starting to form, you're in the proximal domain. And then eventually you start to much more drastically thin this crust as you get into this necking domain. And eventually you get to this very thin, maybe less than 10-kilometer crust where you change the aperture of thinning, and then you're in this hyperextended domain. And then in some cases, you'll start to exhume the mantle lithosphere in this exhumed mantle domain, and then eventually into C4 spreading. And so this is something that we can see once we do these models. And with a lot of these models, they use something called a free surface as their top boundary. And so what this is the surface of the model can deform based off the tectonic forces. And this is important because the faults actually react to this loading that's at the surface. So when you change this, you can get changes to your fault system. And so one of the things with the free surface is that you end up with these unrealistic topographies because you don't have erosion or sedimentation. So this is something where when you add erosion sedimentation, you can redistribute this topography, which then can have an effect on these faults. And so there's been quite a few models that are using these surface processes as well. And this can be done in a few ways. The one way is to add it as just a diffusion equation at the surface. And this is a short range transport of the sediment. And the second one that we saw in the earlier talk is that you can also couple a tectonic code with a dedicated landscape evolution code. And here's also another example of that where we have SOPAL coupled with FastScape. And the main thing a lot of these studies have found is that when you add surface processes onto a rift system, they work to increase the localization on a fault and they prolong the fault lifespan. So the question I kind of want to look at during this talk is, how does the fault network of a rift evolve from inception to breakup? And can we track it quantitatively? And the second that I'm just going to go over briefly near the end is what kind of features can be seen within these sedimentary units that we're developing in these models? And the way we're going to look at this is with the two-way coupling between the open source codes Aspect and FastScape. And I just want to mention that this coupling is now available in the Aspect developer version. So briefly to go over the two codes. Aspect is an open source tectonic code, and its big selling point is that it has this adaptively refining mesh. So as the model evolves, we can mostly just keep very high resolution in the areas we're interested in. So in these cases, this would be near the surface and specifically the sediment. And the second that we heard about earlier is FastScape, which is this landscape evolution code available in quite a few different languages. And then it applies things like marine diffusion, hill slope diffusion, and the stream power law to erode the surface and deposit sediment. So with these two in mind, we set up our 2D aspect model where first we have this 2D aspect model that is consisting of an upper and lower crust and then a mantle lithosphere. And to seed our rift, we slightly thicken our upper crust, which makes it a little bit weaker in the center so we can localize deformation there. We then extend it at 10 millimeters per year with inflow on the bottom to compensate for this. And then the top is deformed through a 2D FastScape mesh, where the way this kind of works in this case is we have our velocities from our aspect surface, and then we copy these along strike to every node on the FastScape surface. FastScape then runs these erosion and sedimentation. It finds this new surface, it averages it together and sends a velocity back for aspect so it can change its surface as well. So we took this model and then we wanted to apply this to all three types of rifts I mentioned earlier to see how the fault network of each one also evolves. And so this is just an example of the symmetric model, which I'm mostly going to look at to keep this short, where we can see Fastscape on top and then the top portion of the aspect model on the bottom. And so as you can see, we begin to form our rift valley in these rift flanks, which we erode and put into the center. And eventually we begin to drastically thin the center crust as we start to enter into seafloor spreading. And then here in black, we can see our accumulated plastic strain, which is kind of our fault system. And so this over here would be the passive margins from these model. And so the other thing I mentioned is that we also want to see if we can see these structures and track them and see how they change in a quantitative way. And for this, we use the Python toolbox FatBox that was developed by Thilo Rona. And so how this kind of works is first we take out our accumulated plastic strain field from aspect. And so this kind of tells us where we have deformed the rock previously or where we're maybe currently deforming it. So we then place a threshold on this and we get these large shear bands that tell us where we have deformed. But this is not the best way because we need this to be discrete line segments for faulting. So we skeletonize it down to these discrete lines. After this, we can, based off a few routines, put these labels on each one and divide them into individual faults. So on this, say, 2-laboral fault, we can then track things like the displacement and the slip rate of this fault. And then we can extend this and track it through time as well to see how it changes. So here I'm going to show a second video that's the exact same model, except for this time we're going to show the fault network through what FatBox has tracked, where black and red and blue will be our active fault network, and then black will be our inactive faults. So you can see we had a lot of faults that quickly localized on 2 major ones, and then we get to a portion where everything is active at the same time, thinning the crust until eventually it becomes thin enough in the center that everything kind of focuses inward, and we deactivate our outer faults until eventually during seafloor spreading, we just have a few short faults that are rapidly replaced. And so we wanted to see if we just look at this active fault network, how does it change through time? And to do this, we look at 3 main things: the displacement on this active fault network, the length, and the number of faults within it. And what we ended up finding is that the fault network actually goes through a number of phases as it evolves towards breakup. The first would be where we have this distributed deformation. So this was that very initial stage where we saw lots of faults competing with each other. And this is when we have a large number of faults and a large length of the fault network. But as we saw, these quickly localized under a few major faults, and then we started to continuously thin the crust and make new faults, but everything was staying active. And this would be a fault system growth phase where we see an increase in all our fault parameters. After this, as we saw in the video, at some point it becomes preferential to focus deformation inward. So the outer faults start to turn off, and then we continuously get smaller and smaller faults, which would be our fault system decline shown over here, where all these parameters decrease towards breakup until eventually we get to seafloor spreading, where we just have replacement of these few small faults over and over. And at this point, our fault parameters remain relatively the same. And so as I said, we didn't do this just for the symmetric model, but we also did this for a wide rift and an asymmetric rift case. And what we found is that for all 3 of them, we saw the same 4 or 5 distinct phases and the same progression through them. The only major difference is that for the wide rift, this fault system growth, where all these faults were remaining active at the same time to thin the crust, lasts a much longer period of time. And then, the second is that when we look at the asymmetric one, we actually have a 4th phase where between this fault system decline and the eventual seafloor spreading, we have this migrating rift. And then something I didn't go over too much for these, but that regardless of these rift types, we found that if we change or add surface processes to them, we see kind of the same things where, as other papers have said, we have this more fault localization and longer lived faults, and this resulted in fewer faults forming overall in a less complex fault network. And so the final thing for this part is I wanted to talk about these rifted domains I brought up in the beginning. One thing we're curious about is, since we have these different phases of our fault network, how they would compare when we looked at also the rifted domains. And we found out there was actually a pretty good correlation. For example, we initially had that distributed deformation phase where you have lots of faults, and this is similar proximal where we're starting to see some structures, but we haven't really significantly thinned the crust yet. And then we get into that fault system growth where we're thinning everything with all these active faults. And this is similar to this necking phase until eventually deformation focuses inward and we enter into this fault system decline, which would be similar to a hyperextended phase, and then eventually into our oceanic breakup. And again, this was pretty similar for symmetric and wide, but there are some differences when we look at the asymmetric case, which is mainly that when we have this migrating rift, we get a very large hyperextended region. And the second is that when we look at the other side, or the side in the direction of rift migration, we can see that we actually don't have much of a passive margin here at all. It just seems to go straight from distributed deformation almost to breakup. And this seems to be because as the rift is migrating, we actually begin to break up this passive margin and translate it over to the other side. So we kind of lose the history that we had here. And then one thing else you might notice about these is that we have a lot of different sediment features that are starting to appear here. And so this is something that we can look a bit closer at. So in these models, we are tracking both the sediment age, and also we have this high resolution of, I think it's about 150 meters in here. So as these evolve, we can actually see the orientations of these basins and see these different features start to form. And so
10 minutes.
Okay, thank you. Some examples of this is, for instance, here we can see that we have this older sediment that has been rotated, and then on top of it, we have started to put this new sediment, this newer sediment forming this angular unconformity. Similar, we had these basins that were active while rifting was occurring, and eventually they deactivate, so we get sediment packages from that. But then at some point, we start to overlap these with the sag basin sediment, and this forms these multiple rift unconformities. And similarly, if we look at one of the initial rift basins, we have this very old sediment that was dormant for a while, but eventually we start to actually put new sediment on it after almost 8 million years of not having any sedimentation, forming this large unconformity. But the nice part about this is with these models, we can actually look at how these features formed over time. So this is a very nice video that Sasha made from this asymmetric model, and I think it shows a good example of these. So initially we start putting a lot of sediment in the center where we just have this large continuous initial rift basin, but eventually as the rift or the crust begins to thin, we start to break this up. And then we start to form these left Younging fault basins while the rift is active. And then over here, you can see at one part, we actually break off a piece of this initial rift basin. And here you can see it being rotated as we're putting more sediment on top. And this forms that angular unconformity we were looking at. And at the same time over here, we can see that we have these basins that are now inactive being, having the sediment from the sag basin being put on top. And this is then creating these rift unconformities. And as we continue, we can see that this fault over here begins to reactivate later in the model, which is then starting to rotate this basin, creating this accommodation space so we can start putting in this new sediment here. And then even here too, we can see that we're continuously breaking up pieces of this. Even this rift now is being broken up and pushed to the other side. And so this is something that we didn't really get a look at in the study, but I think it's just interesting to look at how these different features form and how we can compare them to real world. You can imagine for, say, this basin, if this was subaerial at the time, we could see this tilted large sedimentary unit, and as you walk across it, you come to this large unconformity. I guess we'll just play the last little bit as we see this initial basin being exposed at the surface and continuously being broken up as the rift continues. And so just to conclude on this, when we look at the way the fault network evolves for a rift, just regardless of the different types of rifts they can be, we find that the fault network evolves through up to 5 different phases, and that these phases correlate pretty well to what we'd expect from seismic data of rifted margin domains. And this is something that I'd be interested to compare to the actual seismic data in the future. An example of this is from Boyder et al. 2023, where they looked at this asymmetric model and compared it to the Norwegian margin. And the second is that with this high resolution we can get within the sediments in these 2D models, we can actually start to see a lot of different sedimentary features forming, like these angular unconformities or these other unconformities. So it'd be interesting to, again, take a closer look at how these form and how they compare to what we see in reality. And that should be it. Thank you.
Cool, thanks. Sorry, I was fascinated in what you are saying. Okay, so do we have questions, not in the chat. If you have some, you can raise your hand. Meanwhile, I have a question. Yeah, I just ask it and then Derek can ask this question. On the first part of your talk, did you see an impact or did you make a study, automatic study on the deep angle of the faults, on the activity of your fault network versus the deep angle?
So we did briefly look at the dips. I can't remember. I know we didn't spend much time looking at it, and I don't remember if that's because we didn't find anything or more just. I think it was more that it was just on the back end of what we were going to look at, and we didn't have time to do it. But with this fat box, this is something that we could track as the dip angle to see how it changes.
Yeah, that's it. Yeah, you can track easily the angles. Yeah. Okay, and another question just related to the part of your talk still. So you had a clear signal with the beginning of the phase 5 in your models. Do you know what would be the impact of serpentinization if you could add it in the models?
So a clear signal for the start of the seafloor spreading?
Yeah, when you begin to really exhume the mantle asthenosphere.
Yeah. I'm not exactly sure what changes serpentinization would have. I know that in our models, we didn't actually track this, but we saw that in some cases we would be able to have serpentinization, and this would be more likely in stage or the ones without surface processes, or at least lower amounts of surface processes.
Yeah.
And
that would be interesting to know in the future if we manage one day. Yeah, that would be.
Yeah, it would be. Yeah, I agree. Interesting to see how that changes things.
Yeah. Sorry, so Derek, you can go.
Thanks. Really interesting talk. I saw in the various time graphs, it looked like there was kind of in some of the phases very short, kind of systematic variability and development of the fault network, especially in phase. Yeah, they like phase 4. There's quite like a lot of a lot of variability on the short time scale. Is there any thoughts on that? What's going on? What's controlling that?
Yeah, so this is also probably when we decide whether a fault is inactive or active, we had to set some cutoff on the velocities because otherwise all faults are technically active at all times. And so a lot of this is probably just things just being on the edge of activity and they just blink in and out.
Okay, I think we should move. We have 2 other raised hands. Yeah, Mo, you can begin.
Yes, thanks. Thanks, Derek, for the really good talk and a lot of interesting data actually showing there. I was wondering, can you track with Fatbox? Can you track the kinematic of the faults, like if they are like normal or like if they get reactivated as reverse faults?
When I used it, I don't know if this was something that was already programmed in, but I would think you can because the way the slip rate is calculated, if I remember, it's done so that you take the footwall and the hanging wall and calculate the velocity change. So to assume that you should be able to tell what type of fault it is as well.
Okay, because I was just curious actually to see if there is actually like any kind of like inversion of some of the faults actually, especially the ones that get actually like deactivated for a long period of time and then they get reactivated at some point when you get actually like into the hinterland of the rifted margins.
Yeah, that would be really cool to see. Yeah, I think it's possible with Fatbox.
Awesome. Thanks.
Thank you. Ritske?
Yeah, very nice models indeed. So one of the key parameters in these models are the weakening parameters for both the plastic and the viscous weakening. And these are also among the least constrained parameters. Now, I was curious, have you let some of these models go for some time with oceanic spreading? And have they ever resulted in asymmetric spreading? Or, I mean, the reason I'm asking is that we did a exhaustive study on basically exhumation of mantle with Thomas Teunissen a while ago, published in Nature.com. And if the weakening is too large, either the brittle, I mean, we didn't include viscous weakening, but it would also add to that. If we have too much weakening, we get asymmetric spreading. And so that was actually a reason to discard these models and to limit, basically have at least some bound on the degree of weakening. So I was curious, because in your models, you have quite significant weakening. It's not only the I mean, you have 75% of viscous weakening, I saw in one of the slides. And similarly for the I guess for the brittle or plastic parameters. So did you ever observe asymmetric spreading after breakup? Or did you stop the models as soon as they as soon as the crust basically did you not let them go that far?
Yeah. We ran them for a while after breakup. I can't remember if after breakup we ever got any asymmetric ones, but I don't think it's something I was also directly looking for, so it could have happened and I wasn't noticing it. I do remember in some of the wide models, and maybe as you said, this is because we had such high weakening, some of them would actually start to migrate before they officially broke up as well, which was interesting to see. And similar, I know for the symmetric model, we did reduce the amount of weakening to get it to be more symmetric. But yeah, I would have to look back at the models to see, and that would be interesting to see whether that happened.
Yeah, a long time ago, when I combined both viscous and plastic weakening models where we had both developed highly asymmetric margins. I mean, it's in paper published in 2003, and they were become so asymmetric that we decided not. This was one of the reasons to not include viscous weakening, or at least not let it play a large role. But I guess, I mean, I guess the verdict is out on that.
I think we will just take one last question because he waited a long time. Valentin, if you want to ask your question.
Yeah, thank you. Thank you for this very nice presentation. I have a more general question from someone that is not a specialist at all about modeling. Is here you show this beautiful model that combine tectonics and sedimentation, but they are all magma pore margins. Would you be able to do such kind of modeling, including magmatic intrusion, also early in the rifting phase? Like I'm working in the Alpha depression, and there it's a big topic. What is the components of tectonics and magmatic intrusion? So is that possible to imagine some models with also intrusions?
Yeah, so this is really interesting. I'll speak from Aspect because I don't have as much experience with the other codes. There is some melting. I'm not sure how well it is with lithosphere scale stuff yet, but it's being developed. And I know it's a big thing that a lot of people want to get this in here and start having these different processes. But yeah, I'm not sure. When we did this, I don't think it would have been available now, though. It's maybe closer, maybe it is available. I'm not exactly sure.
Thank you.